Our next presentation, Jason Evans is going to talk to us about bushfires and climate change. So please welcome Jason.
Good afternoon, everyone. So I'm a climate scientist. I spend most of my time studying how the climate system works, particularly how it works at regional and local scales, and how global changes in the climate system are manifesting themselves at these kind of scales, including the impacts on different phenomena. And one of those phenomena I'm going to talk about today is bushfires. So I don't have pictures of cute butterflies or things, unfortunately. I'm going to first talk to you about a bunch of things we know when it comes to climate change and bushfires, and then I'll talk about a few things we're still trying to work out. Apparently we need to go to the first slide.
I'll get you there.
Okay. All right, here we go. All right, so the climate is changing, and it's changing at a global scale. So this is really well known now. Okay, you can see the figure on the right there. That's just the mean global temperature over the last more than a century. And you can see we've got a fairly consistent increase. And in particular, since sort of the middle of the 1900s, we've seen a very consistent increase in global temperatures. Now, this is observed in lots of different ways. It's really well established. A few things to note is that this warming, it's not evenly distributed around the globe. So there's some parts of the globe that are warming faster than other parts. And in particular, the northern Arctic regions have been warming faster than the rest of the Earth. And it's worth noting that pretty much all land regions are warming faster than ocean regions. So when you talk about a 1 degree global average warming, that actually translates to more like 1.5 degrees warming over land and 0.7 degrees warming over the ocean, something like that. And we know that this is caused by the way we're changing the atmospheric composition, and that's what we're doing by burning lots of fossil fuels effectively, right? So this is all really well known and established facts. That's thinking about the globe. We can also look at what our climate records say locally. So here's the Sydney record from Observatory Hill. We've got, well over 100 years of record here. If you look at the temperature record first on the right there, it looks fairly similar to the global picture, right? Like a fairly consistent increase in temperatures, perhaps more consistent since the mid-1900s. So it's quite consistent around the globe that this is sort of the local manifestations of that global change you see. On the left, we've got the annual rainfall totals, and there's not really a trend in that rainfall totals. What you can mostly see is that we have really big year-to-year variability in our rainfall, right? So from the highest year of more than 2,500 millimetres to the lowest year of about 600 millimetres. And that range is really unusually wide for most parts of the world, so they don't see that much variability on a year-to-year basis. And that's kind of a bit of a defining feature for a lot of Australia's climate, is that we have this very high year-to-year variability that defines a lot of our aspects of our climate. And that becomes important when we think about some of the phenomena like bushfires, that variability. Okay, so I'm going to give you the bit of the punchline straight away. So the climate is changing, and that is changing things about bushfires and the way they develop and spread, okay? So lots of research has been going into this, and we know a whole bunch of things about this already. So for one, the fire weather gets worse as the climate is changing. So the fire weather being the days where you have weather conditions that are really good for fires and for spreading fires. We know that the fuel loads are increasing. So when a fire does come along, there's a lot more fuel there to help it spread and become more intense. We know we're getting longer and hotter heat waves. So if you've got lots of vegetation, we get these longer, hotter heat waves, they dry the vegetation out more, and that makes the vegetation much more likely to burn. We are active in trying to manage the landscape. We do prescribed burning on a regular basis here in Australia. we do this in very particular times of year. You have to have the right conditions. They can't be conditions that are really good for fire because you don't want to prescribe burn to get out of hand, but they have to be conditions such that a fire will actually burn. It can't be very wet and all that kind of stuff. So there's very particular conditions. And what we're seeing is that those conditions are changing in terms of the time of year that they're happening. And this has implications for the fire services and how they use their resources. And lastly, I'm going to talk about conditions suitable for what's known as pyrocumulonimbus or firestorms from happening. Now, I'll get into this more. These are really extreme, very dangerous forms of fire that have become much more common in recent years and didn't really exist very much several decades ago. And I'll show you some of that information. Okay, so I'm going to go into a little bit of detail of each one of these. Okay, so first one about fire weather and how extreme we're getting more extreme fire weather days. So here's some work we did with the New South Wales government using the Forest Fire Danger Index. So this is an index that combines measures of temperature and humidity and wind and the drought conditions as well to come up with an estimate of how likely the surface weather conditions are for fire to spread. And if it's over 50, it's considered an extreme fire weather day. You've probably seen these meters near national parks and things that show you this. On the really bad days that you might remember, like Black Saturday and during Black Summer, we sometimes get over 100 in this index. So these are really catastrophic fire weather days. Nevertheless, what we see is with climate change, we see a consistent increase in the number of these extreme fire weather days. So the days where if a fire were to start, it would probably spread quickly and be uncontrollable fairly quickly. Okay, so these are quite bad. It's not evenly. It's not everywhere is increasing the same rate. As you can see in New South Wales, when we're near the case, we're seeing smaller increases in the number of these extreme days, but we're seeing much more as you head west and north. Okay, let's look at fuel loads. Okay, so the weather conditions seem to be more conducive for fires. Of course, fires can't burn unless there's fuel there for them to burn. So what's happening to the fuel? So we look at this a few different ways. Here we're looking at records taken from satellites. They're orbiting the Earth, looking down all the time, and here we're just looking at how much green vegetation the satellite is seeing through time. So this is over about 40 years. How much has that amount of green vegetation changed? So it's like the leaf canopy cover that they're looking at. This is the part of the plant that's doing the photosynthesis. So photosynthesizing means the plant's growing, it's creating more fuel. Okay, and you can see over Australia, and this is true actually for the majority of the world, that over these long time scales we're seeing consistent greening across the landscape. There is a few little tiny patches where it's an opposite trend, but it's a bit hard to see because there's just so much greening happening across Australia. So what we're seeing, even though we've had, over these 40 years, we've had lots of droughts and we've had flooding periods and all that kind of stuff, consistently over time, we're seeing more vegetation growing across the landscape in general. Okay. So that's the vegetation in general. Then we also looked at, in particular, the vegetation that would qualify as fuel for fire. And we get a picture that looks like this. So part of the reason we're getting this widespread greening is called CO2 fertilization. Of course, in photosynthesis, the plants are taking in CO2 out of the air, and that's fueling the plant. We have higher concentrations of CO2 in the air. It's easier for the plant to do that. Okay, and that's what we've been doing. We've been increasing the concentration of CO2. Makes it easier for the plant to do that, and so they do. They do it more. That's why a strong reason why we're seeing widespread greening. And it's one of the reasons that we get this result here, where when we look particularly at the part of the vegetation that's fuel for fire, we see a similar trend of widespread increases in that fuel. What I'm showing on the left is two estimates. There's uncertainty around how the climate is changing and will change. So we have a low-end estimate and high-end estimate. And you can see even in the low-end estimate, there's significant increases in the fuel for fire that we can expect as the climate changes. Okay, so we're getting more days that are conducive for extreme fire, and we're having more fuel available when those days occur. Of course, it's not enough just to have lots of vegetation. If it's wet, it's not going to burn, so it's not an issue, right? It's only an issue once we dry it out. And the best way we have to dry it out is to have some heat waves. And we've been having a lot of heat waves. So if you look at what's been happening, we've seen increases in the duration and intensity of heat waves over the last 50 plus years. If you look at what's projected to happen with climate change, which is what I'm showing over here, again, you're seeing projected increases in the frequency or the number of days under heat wave conditions and how long an individual heat wave will last, the duration of that heat wave. So we're seeing these heat waves happen more often, last longer and be hotter. So it means if we have the fuel there, we're going to have periods where that fuel is really dry on a more regular basis than we have had in the past. Okay, so we're not passive in this situation. We can do things to try and protect ourselves from fire. One of the things we do is prescribe burns. What's happening to the conditions we need for prescribed burning? So right now, the vast majority of the prescribed burning we do in March, April and May, and a little bit happens in August and September. So March, April and May, that's actually at the end of our main fire season, when they tend to do that. And you can see on the right, we have a map for each month where the red shows that we have fewer opportunities to do prescribed burning, but the blue shows you have more opportunities to do prescribed burning. So what you see is in the months where we do most of it now, we're going to have fewer and fewer opportunities to do it. But in months closer to the winter time of year, to the cooler season, we'll get more opportunities than we did before. So here, the story here is really about being prepared to plan for this change in the timing of when you can do this. Now, the problem for the fire services here is that we actually share a lot of resources when it comes to fire suppression, firefighters and firefighting equipment with North America, because their fire season is in our winter. So often many of the volunteer fire services or people and their equipment actually go to Canada and North America in that period, which will become the period that we will want to do prescribed burns. So that could be an issue. And lastly, and possibly most interestingly, I think, is these firestorms that we're starting to see. Now, these are devastating events when they occur, but just from a physical atmospheric scientist perspective, they're absolutely fascinating events. Now, you might have seen images of these kind of events. I don't know. So here's a few images of different ones that have occurred just in the recent decade here in Australia. So what you see is they transition from being a regular fire where you have a smoke plume coming up and getting blown by the wind to actually developing a deep cumulus convection cloud where the updrafts are being driven not just by the fire anymore, but actually by the storm system, the condensation of moisture and the storm system that forms, and they form deep cumulus clouds above the fire. It's actually a mixture of the fire, smoke and these cumulus clouds that develop. And then they themselves can produce their own thunderstorms, and which changes the local winds and changes then the development and progression of the fire and feeds back on itself. These kind of events cannot be suppressed. So whenever a fire reaches a stage like this, the fire services have an evacuate procedure for the firefighting personnel. So they would have told the general public, all of us, to evacuate well before that. But if the fire ever reaches this stage, it's evacuate for all the firefighter personnel as well, because there's nothing they can do and the spread can become erratic for a number of reasons. The little orange graph down there shows you the cumulative number of these events that have been witnessed in Australia since the 80s. And so we had one in 83, that was Ash Wednesday. People might have heard about that one. And it was kind of the only one that was witnessed for kind of over a decade. And then we had a few occur, and then we had a few more. And you can see there's been this steadily increase in these kind of events until the 2019-2020 Black Summer season, where we saw almost as many in that one summer period as we had seen in the previous 3 decades. So these events have gone from something that were really rare, kind of a once-in-a-decade event, to something that we can be seeing many times in a fire season. And they don't spread the way traditional fire spreads, and we don't understand them well enough to be able to predict their behaviour. And that's one of our issues that we have in fire science right now. Here I'm showing you a view from space. There's a satellite looking down. We're looking at the Sir Ivan fire in 2017. You can see the smoke plume from the fire there. And what we're going to see is that it explodes from a regular fire into a pyrocumulonimbus over a matter of hours. Each one of these snapshots is half an hour between each one. And if you just watch the sort of source of the smoke, any minute now, you're going to see it suddenly explode into a pyrocumulonimbus. Here it goes. There you go, just like that. So these things go from a regular fire to pyrocumulonimbus in less than an hour, right? Which is one of the reasons they're so hard to try and suppress. We've looked into the atmospheric conditions that these things happen in, and we see the results here. Basically, that climate change is increasing the number of days when the conditions conducive for this kind of explosive fire are happening. So not only do we have surface fire weather conditions, extreme surface fire weather conditions happening more often, we have these atmospheric conditions happening more often as well. So it looks like we should expect to see more of these events going forward. Here's a schematic of what kind of happens in these events. So we have has to be a fairly big fire at the surface, generating a smoke plume. As it rises and cools, there's some water in the smoke. A lot of that is often from the vegetation being burned. It actually has water in it. It condenses, and that generates a stronger updraft. It eventually becomes cloud. You can see it switches to white colour there. That's because now it's dominated by water droplets and ice crystals in the cloud. This then can generate its own storms. You can get big downbursts, which then give you different winds at the surface, part of the reason that they become very hard to predict the spread. You can get lightning from these things. The lightning can then start spot fires ahead of the fire. And the questions we have is, with this sort of schematic in mind, what do we understand about how these things will change with climate change? So one thing we already know is that we're likely to have more fuel, right? So if we have more fuel, we can probably expect the fire that's burning could be more intense, and that'll give us a stronger updraft. If we have a stronger updraft, then we can probably end up with higher clouds, deeper convection. That likely leads to stronger storms. That means we could have more intense downbursts, which is then, again, giving us these erratic winds at the surface. Could mean more lightning associated with that because we've got deeper convection, which means more ice in the cloud, which tends to give us more lightning. And one important thing in Australia that's missing from this altogether is the generation and shedding of burning embers. And we've had cases in previous years where fires were started by burning embers more than 10 kilometres in front of the fire front. So if we don't consider what's happening with these burning embers, we're not going to be able to understand the ways fire spreads in Australia. And so all these question marks that I've got here, these are topics that myself and others in the research of these events are looking at right now to try and better understand how these processes work and how they might be changing as our climate is changing. So as a little summary then, I've shown that climate change is impacting bushfire occurrence and spread, and those impacts happen in lots of different ways that all sort of come together to impact bushfires. We don't know everything. We're continuing to investigate a lot of what's going on with a focus on these really intense firestorm type events. Now I know that this kind of talk, it's a bit of a doom and gloom downer kind of talk, and I've been told that I shouldn't end with a doom and gloom summary slide. So I want to suggest that not everything about climate change is necessarily bad. Change is change. It's not always bad. So I'm very hopeful that climate change might lead to more rainbows.
Thank you for your talk. I have recently read that there is a suggestion of contention about planned burnings, that it might be having the opposite effect of what's desired by actually drying out the land a bit too much and causing more dryness and actually more fuel. I just wondered what your thoughts were on this, if you'd heard of it.
Look, there's a number of contentious issues around prescribed burnings. There's lots of different decisions which are very subjective that they make around doing it. Fundamentally, if there's no fuel, the fire can't burn. Right? So if you do prescribed burn and remove the fuel, then the fire can't burn. Now, prescribed burns are done in controllable ways, which means what they really are doing is burning the lower canopy, the understory. They're not burning the tree canopies. Okay? So what they're able to do is they're able to stop small fires, because if the fire gets big enough that the canopy catches, prescribed burning hasn't had any effect on that. All right, so they have limited impact when you think about the really big severe fires. But what they do is most fires start as small fires. The ones that become big severe fires, they started as small fires. So if you had an area that had you done some prescribed burning and there was no available fuel and then there was lightning there, it wouldn't be able to start that small fire. Yeah. So that's the fundamental basis of it. There are lots of contentious issues around it, though. I absolutely agree with that.
Over here first, if that's okay.
Are there non-climate change related activities that can be done to decrease the danger from bushfires?
So there are. So the main one is to separate the things you care about, your assets and your people, from the fuel that burns. That's the main one, right? So that's the idea with prescribed burning. They try and do that. But that's also the idea about lots of the rules they brought in about having gaps between your buildings and the forest line and that kind of thing. Now, if you're outside the city in Australia, you're basically near bush, right? Like you can't separate yourself that much. So even in the places where they try and put in big breaks, 100-metre breaks, it won't stop the extreme fires. So it's only a thing to stop the small fires. Keep in mind the Australian landscape is a fire-adapted landscape. Most of the species that we have, the eucalypt species in there, they survive fires, extreme fires. Some of them depend on fire to actually germinate. Right? So fire is a natural part of our landscape. And I think there was maybe an old school view that we could somehow try and eliminate fire from our landscape, and I don't think that's realistic in any way, and we shouldn't be doing that anyway. We need to be able to understand how we live with fire in a safe way.
Hi Jason, we had a panel yesterday afternoon whose area of expertise was about vaccines and epidemiology and so forth, and they were recounting how they were getting trolled in a fairly major way, and I'm just wondering if you and your colleagues have had comparable kinds of experiences.
Well, I'd say as a climate scientist that works in a climate science centre, we have had not so much in recent years, but in the past, periods where there was a lot of death threats and things being sent to the scientists. Our lab, which is essentially just offices had a security door installed with a system that wouldn't stay open, so you couldn't be open to the public because of this kind of thing. So yeah, I think anyone who's been in the climate science business for a while has had things like that. You know, on the other hand, you know, some of these skeptics that have their own TV shows talk about us as well. So we become famous in some places thanks to them.
I have a question here.
Me?
Yeah.
Okay. Why is it that I never hear any argument about the effect the biggest heat source, the sun, has on our climate? We're dealing with a total open loop system. It's not thermostatically controlled. It has a great deal to do with the irradiation of the ionosphere, which gives us high frequency communications around the world, which varies all the time, but never a mention on what the sun might be doing. We always blame man's CO2 and all these other aspects, which I don't disagree with. But I never hear what I would consider one of the most critically important issues.
So, well, thanks for your question. And yes, the sun is a very vital part of the climate system. In fact, it is the energy source for the climate. And the climate that we experience and the weather we experience day to day is basically driven by a combination of the energy from the sun and the fact that we're on a rotating sphere, right? And the fluid motion of the atmosphere and ocean on a rotating sphere. So the energy from the sun is definitely part of it. Why do we not talk about it in terms of climate change? Because the energy from the sun has variability on the order of 11 years or 22 years, depending on how you count it, with the sunspot cycle. And that variability is on the order of a fraction of a % of the energy, and it goes up and it goes down. Yeah. Climate change, on the other hand, as I showed you in terms of the temperatures we have here, has been going up for 100 years. So it's the sun's variations can't explain that. Yeah. So it's not part of the explanation for why the global climate is changing.
Question down the front, I think.
Yes, we actually have an online question. So are these fire events, are they more destructive? Do they, for example, burn deeper and kill the tree roots and plants so the trees and plants can't regenerate?
Yeah, so the firestorm, pyrocumulonimbus events I'm talking about, absolutely. They are the most intense fire events that we see. They burn entire forests. There is not a leaf left on a canopy. There is, I don't know if people travelled south after the Black Summer fires. There were sections along the south coast where the eucalypt forest was kind of, stumps sticking up, and that was all that was left. Eucalypt trees have an amazing ability to regenerate, and they regenerate in a fascinating way, putting out little branches all along their trunks. But yeah, these events absolutely burning way hotter than a regular fire event that we have been used to.
It's time for the question.
All right, thank you.
A round of applause for Jason.